Thank you, Simon, for that excellent snapshot of where we are in Australia. So now we're going to take a bit of a detailed look at 3 companies within Australia. So first of all, I'd like to introduce Dr. Cibby Pulikkaseril. Sorry, I thought I could say it if I just look at it. Pulikkaseril.
It's close enough.
Pulikkaseril. Sorry, I was trying to look at you, but I need to see the name. So Cibby brings with him 20 years of experience, and his work in developing optical sensing technologies stems in R&D at Finisar. There he led technical teams for developing innovative technologies and saw them through to commercialization. And he's taken that and started Baraja, which we'll hear about now. So you have your microphone. I'll leave you to it.
Great. Thanks very much, Sarah. Great. Thanks, everyone, for coming. We're really pleased to be able to host you here at Baraja. We've been here since 2020, and if you've ever visited us before at our previous site, which was at Linfield, you'll know that this is a much more open, welcoming space. The talk that I'm giving is, I call The Road to Infinite Resolution. We call it Baraja Spectrum Scan LiDAR, which describes the way that we steer the light in LiDAR. And this is a talk that I've been giving recently to some industry groups. So I gave this same talk at Clio last week or 2 weeks ago. So about us, so we founded the company in 2015. I was working with Simon at Finisar, and I quit in 2015 to start Baraja. My co-founder Fed and I quit, liquidated all our savings, put it all into the company, and started in his garage. That was a bit of a terrifying ride. But since then, we've grown the company to 150 people, most of which are here in Australia. We've got people, an R&D team and business development in San Francisco, and we've got a couple of people that are in Detroit, Shanghai, and Sweden as well. All right, so spectrum scan, what does it mean? Well, we've put this little animation. I'm going to click it, right? Oh, yeah. So if you put white light through a prism, you get this rainbow that comes out of it. That's because white light has all the constituent colors. So if you put a single beam of light at a single color, you'll get a unique angle that steers out of that prism. So in fact, you are steering this beam just by changing the color. And that's what we do at Baraja, but we don't use visible light that you can see as a rainbow. We use the infrared wavelengths. Normally we call them the C-band. These are inherently eye safe, and we can generate them with telecom components, but we do the same thing. We change the wavelength of infrared light, put it through prism-like optics, and use this then to scan the environment. And we do that with no moving parts, and we're the only ones doing this. And that gives us the ability to steer a beam with no moving parts. So how do we do that? We've got these very fast tunable semiconductor lasers. These are things that I learned about when I was at Finisar, but these are common in telecom, and we've now repurposed them into LiDAR. We use prism-like optics to steer this beam, and so these are fixed passive pieces of glass. And by steering the beam without moving them, they are inherently reliable. They can be cost reduced. They can be very small. Then the ranging that we use, instead of using very narrow pulses, which is what most of the competitors do, what we do is we call it RMCW, Random Modulated Continuous Wave. We send out a code, and when that light bounces back and we detect it, we check that it's our code, and we can measure the distance to a target based on the delay in this code. What does that do for us when you can steer a beam with no moving parts? Well, if you take a look from inside the prism, you can see that each of these wavelengths corresponds to a line, a horizontal line. And so the more wavelengths that you play, the more lines you get. So by increasing the number of colors that you're shooting from your laser, you get more and more wavelengths or more lines, so you can get infinite resolution. We do this without any moving parts, so actually we can control which colors we play. That allows us to move the concentration of beams up or down in the field of view. So you can focus the attention, and this is actually key to an artificial intelligence that wants to understand what it's looking at. So you can see there, for example, that the car can decide to focus at the horizon, or it can look over the entire field of view. So the talk that I'll give now is I'm going to talk about how we solve at Baraja these 3 problems: range, resolution, and interference issues. These are all problems with traditional LiDAR. These traditional LiDARs are being used today. Companies like Waymo or Google or Uber, when they had self-driving operation. And you'll notice that they sit on top of the car. They're big rotating elements. These traditional LiDARs all have the problems. They don't see far enough. They don't have enough resolution, and they interfere with each other. This is the result of surveys that we've done with a whole bunch of customers, suppliers, and competitors. I think it's about 100 people we talked to, where we got them to tell us what was the most important thing that they wanted to see in a LiDAR. And you can see that's what reflected there. They wanted most of all range. Second, resolution, and then third is cost. So that is like saying that they would pay more for range. So let's talk about range. So since we're all optics people, I thought I'd put this in context. There's a very nice paper by Fersch and his co-authors. That's a team out of Bosch. They published a paper in 2017 which describes how far can a LiDAR see without damaging the human eye and being limited by some other physical properties of the LiDAR. And this equation is something that we use really often. It's called the LiDAR range equation. And it relates how much power you receive, PRX, from the power you transmit, which is PTX. And then there's this factor in front of it, which is a combination of many things. For example, how much light can get through your LiDAR, the reflectivity of the target, the aperture that you're receiving photons through. But most critically, you can see it's inversely proportional to the square of the range of the target. And this is really one of the huge problems of LiDAR, that you may say, well, I've got a LiDAR, it can see 20 meters, fine. I can see 100 meters, fine. If you want to go from 100 to 200 meters, which is how far our Baraja LiDAR can see, it's 4 times as hard. And so we've developed our LiDAR to have better effective range. So not only can we see intrinsically further, but we have the resolution that makes this actually feasible. So you can see in this picture, we've accumulated a whole bunch of scans to show what is the natural resolution of the system. You can see that it's very highly detailed. It's almost like a 3D image. Here's an example from one of our vehicles driving across a bridge in San Francisco. This is an example of a point cloud that's live at the native refresh rate that a car would use it at, which is usually at 10 hertz. And you can see that as you get further and further away, I mean, it's very difficult to get points on target, but our ability to concentrate the beams at the roadway allows us to track these vehicles past 200 meters. So that's a demonstration of the range that we're able to provide to customers. All right, so then resolution. How do we achieve resolution? Or what's the trick about resolution is pretty interesting, actually. This is something I've taken out of a talk I gave at OFC, which is one of the problems with resolution is if you try to meet all the customer requirements, you'll get to a pretty difficult problem, which is you take the horizontal field of view, they want 120 degrees. The vertical field of view, then they want 25 degrees. And they want 0.1 degree resolution in both axes. And they want that 10 times a second. So when you calculate that, that's 3 million points per second. The problem is, I said, the range that we see is 200 meters. The maximum range we detect to is 300 meters. Light will take 2 microseconds to travel 300 meters and back. Simple calculation. So that's the time it takes for you to measure one of these points. How many of those can you do in 1 second? Well, it's just 500,000 points. So that tells you there's a problem. 500,000 is much less than 3 million points per second. And though I said those are the requirements, I mean, actually customers are asking for much, much harder resolution requirements, 0.05. And so you can get up to numbers where you're almost at 20 million points per second. These don't make sense. The way we deal with this is because we don't have to move anything to scan the beam, we can change where we're looking. And so here's an example of a point cloud. We've got a guy walking down the street, and what we're doing is we're cycling our resolution, having heavy concentration at the top and moving that down. Because you have to realize the only place you need to really have long range is at the horizon. So as the car moves up and down the geography, if you can focus your laser beams at the horizon, you can guarantee you get a certain number of points on target, and that's what the customers care about. Everywhere else, you can be coarser. I'll demonstrate this. This is an example of what we can achieve sort of at the maximum, which is we are going to scan 1,000 wavelengths, and we'll accumulate this over many frames to show what this looks like. This is at a marina in San Francisco. And I think this is a good demonstration of what we're trying to achieve at Baraja, which is having very good native range, near infinite resolution, but also we've got a wonderful optics team represented by people here that you can meet. They work really hard at making sure we have very good beam collimation. So that beam is tight and collimated all the way out to 200, 300 meters. Okay, and I wanted to go to this one. Finally, I'll talk about interference. Interference, so that's not on the top 3 items that we asked customers about. And that reason is clear because not many people have a whole bunch of cars that are self-driving. So if you talk to people with 1 or 2 vehicles in their fleet, yeah, they don't have interference problems. Or they might notice it when they measure on the bench. When I talk to customers that have 100 vehicles, this is a huge problem. And the problem is you have 2 kinds of interference. You get lidar to lidar interference where they point at each other. Some of the early lidar systems would then get damaged by this. Today, all you get is what we call false positives, just really bright flashes that you can't expect. The second is this scattered interference, that if you have 2 lidars looking at the same object, if that is a reasonably bright object, you are getting returns from both of these shooting at each other. And then these also contribute to false positives. These are unwanted measurements that you cannot really afford to have. What does it look like in a point cloud? This is from a paper in 2020. This author took a LiDAR system at the axis coordinates 0, 0, and then put one off to the side, the same type of LiDAR, turned them on, and this was the point cloud you get, where the green points are the correct ones. The red ones are the false positives. So this is just with 2. You can imagine what happens if you're saying you're going to have 10 or 100 vehicles on the road, then this is unusable. At Baraja, what we do to fix this is the same thing we use to steer a beam out, gives us protection from interference, because every color is mapped to a unique angle. So if you go out with blue, it has to go out and back with that same angle. Any other wavelength at any other angle will not couple back. That's our inherent immunity to interference. The second point is I told you we use coded modulation. So, you can get 2 Baraja lidars, they don't really interfere with each other. However, you can get the wavelengths to line up right at the horizon. In this case, the lidars are coded with different modulations. So even in that case where they do line up, these codes don't propagate. So we don't get a false positive. We are immune to interference. Great, so those are the 3 things I wanted to talk about, what we are doing at Baraja to really address what customers want. And I hope that we are going to have very significant customer news this year. What we have most recently is we've announced that Hitachi has invested in us, and they're using us for their autonomous mining operation. And I want to show, this is a video from Hitachi. This is one of their large excavators making these autonomous, and you see here. These are controlled by remote operation, so there's not a driver inside. But they are working to make them. You can see the blue Baraja lidar there on. We are working with Hitachi to provide them with lidars for their autonomous fleets, excavators, dump trucks, the whole range of mining equipment. Great, and I'll end there. Thank you very much.
Thank you very much, Cibby. Questions from the floor? Yes.
Thanks for the talk. It was really interesting. I just have a question on how does environment condition like rain or fog, for example, affect the resolution and interference, and how do you deal with it? Thank you.
Great question. So how do environmental conditions affect LiDAR? So typically, the same things that you can see that affect your vision, they affect LiDAR. So when you have very heavy snow, yeah, it will impede how many points you get back. Typically, though, some of the what we call flash lidars, some of the short range lidars are very badly affected by snow. Because we scan each point sequentially and we have very good beam combination, we tend to shoot through rain and snow really well. So in general, I think we perform much, much better in those kinds of weather conditions. And in fact, we've done a demo in China where there was a typhoon, and so we call ourselves typhoon proof. Now, the one weather that is a problem is fog. Fog is, it's sort of impenetrable to the human eye. Light doesn't propagate through fog. In those cases, that is why those vehicles, they need to use a radar for those use cases.
All right, we've got time for 2 more questions. Any? To run around.
Hi, just a really quick question. I'm just curious if the measurement that you make, is it all close to being shot noise limited, or are you limited by all sorts of other noises?
Very insightful question. I mean, I would say there's lots of other limitations there. Yeah. Maybe I won't dive into exactly what we're limited to. Yeah.
Do we have an online question? No, there was one more hand I saw. Otherwise, I'll start. Okay.
Yeah, thanks a lot. Fantastic presentation. A couple of years ago, Elon Musk mentioned that LiDARs are sort of not necessary for a lot of self-driving situations, but I guess that's probably because they're too expensive at this point. Like with your technology, is there like in the future possibility to significantly reduce the costs for the systems?
Yes, in fact, what you'll see is the cost of LiDAR has been decreasing year over year. And, Baraja, we are engaged with several automotive customers. The cost points are very, very aggressive, and we'll bring it in line to be extremely attractive to put these into vehicles. Yeah, there's definitely that pressure.
There's actually 1 more minute, so I'm going to take a privilege of chairing. What, in the 5 years that Baraja has grown, what do you think has been the biggest challenge for you?
The biggest challenge?
Or what has stood out as like, man, that was so hard? Probably everything, but if you had to pick one.
Yeah. Well, look, I'll say because I'm really technical, I used to worry that all the problems were technical. Those turned out to be some of the smaller problems, unfortunately. Yeah. Our problems they're always going to be problems with people, like hiring enough people, organizing people, communicating to people. That seems to be most of my week is dealing with this.
So people.
Yeah.
Excellent. So with that, we'd like to thank you, Cibby, for your time and obviously for hosting us.
Great.
I am apologetic again. I did practice your name several times. Thank you very much, Cibby.
Thanks very much.